Hello, my name is Muhammad Asnawi Azhar, and I'm from Bachelor Degree in Computer Engineering in UniMAP, and I'm from the fourth year. So today I will be talking about my deep learning model that I have recently developed. So the dataset that I use is brain tumor classification (MRI). The reason for this is because I think there is a critical need for an automated, accurate, and efficient brain tumor classification system so we can assist medical professionals in making faster and more reliable diagnosis. So we will move to the development part. The first part that I will be explaining is the pre-processing methods. So the dataset is located in the input brain tumor classification MRI file, and inside it consists of two folders which are training dataset and testing dataset. Each dataset contains four categories of images, as we can see here. The four categories are no tumor, glioma tumor, and meningioma tumor, pituitary tumor. Image processing steps, the dataset was loaded using OpenCV, and images were resized into 150 by 150 pixels. Images were normalized by dividing pixel values 255 to scale them between 0 to 1. And then one hot encoding was also used, as we can see here. We have one hot encoding to label for multi-class classifications, and the data was split into training 80 to percent training and 20% testing. So as we can see here, this is just the visualization of the training data, class distribution in training data, and here we have the pie chart, and also this is the display of images from the training set. So we move to the classification algorithm that we have used. The model architecture that we chose was convolutional neural network. A CNN based deep learning was built using the sequential API in Keras, 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 I mentioned it, Keras. In this CNN model consists of four convolutional blocks for feature extraction, batch normalization to stabilize training, max pooling layers to reduce dimensions, dropout layers to prevent overfitting, and also fully connected layers for final classifications. And then we move on to the evaluation methods. Where do we have the evaluation methods? Yes, here is the model evaluation methods. As we can see here, the first evaluation method is accuracy and loss analysis. This is the coding for the plot training, to plot the history training. The purpose of this method is to track how well the model is learning over time and helps to detect overfitting and also underfitting. Okay, what we can find from this output or from this graph. Okay, as you can see here, the validation accuracy is unstable, and the reason for this, I think, might due to the fact that the model might be overfitting somehow. At the same time, the validation loss is also fluctuating, which means the model is struggling with generalization. I have prepared a few solutions, which is I think we should increase the dropout to reduce overfitting, or more data augmentation to make the training more robust. The next evaluation is confusion matrix. This is to visualize how well the model classify different tumor types and identify misclassifications. From this output, as we can see here, the confusion matrix that we got, meningioma tumor is the most misclassified, as we can see here. The possible reason behind this is because it shared similar visual features with glioma tumors. And I think the solution for this case would be to introduce more high quality training images for meningioma tumors But we also can use class weights to force the model to pay more attention to meningioma. Last but not least, the precision, recall, F1 score, and accuracy. As we can see here, this is the output, and also this is the coding for the output. What we have found from this is the accuracy is 85%, which is quite a good performance. Macro average F1 score is 85% balanced across all classes. Weighted average F1 score is 85% also, weighted based on class distribution. What we have found is the best performance is pituitary tumor, which has 92% F1 score, and the weakest performance is meningioma tumor, is meningioma 75% F1 score. The cause for the worst performance, which is meningioma tumor, we, as mentioned before, is due to the lack of training examples and similar visual patterns as glioma. The recommendation to mitigate this problem is to increase the number of meningioma samples in training and also fine-tuning hyperparameters. So, in conclusion, I think overall this model performs well with 85% accuracy. While this model performed well with pituitary tumors, for now it struggles with meningioma tumor. There are numbers of improvement that can be made to better this model. So, thank you for watching.